Welcome back, everybody. And we're going to continue our exploration of aromatic compounds today. Getting into chapter 22, which is called Electrophilic Aromatic Substitution. Electrophilic. We're going to learn certain electrophiles can be induced to react with benzene or other aromatic compounds. That makes the aromatic compound a nucleophile. And we're going to replace a hydrogen with the electrophilic group. So here we see a hydrogen in the beginning that disappears during this final step here to make our new group be the only substituent on this carbon here. And as we discussed earlier, benzene is very reticent to react because it has a special kind of stabilization. Do you remember what that stabilization was called? And you're thinking, you say, oh, something about resonance, something about a special kind of resonance, something about having the right number of pi electrons and being able to resonate in a circle. Oh yeah, it's aromatic resonance stabilization energy, which we short form to RSE. And you remember that was good for 152 kilojoules per mole of energy for 6 pi electrons. That meaning that these 6 pi electrons are 152 kilojoules per mole more stable than any individual 6 pi electrons that are not interacting with each other. So that's a lot of stabilization. As we saw at the end of last lecture, not any electrophile can do this reaction. They have to be really strong electrophiles, super electrophiles. In fact, you're going to see today the generation of these electrophiles starts with a strong electrophile already and then makes it even stronger. And to do so, you've got to force your electrophile to first be a nucleophile. Wow, that doesn't make sense, but it will hopefully when we get to our next page. Now, looking at the overall reaction, could you predict whether it's endothermic or exothermic going from the beginning to the end? And the answer is not really, we don't really know. It depends on the strength of the CH bond versus the CE. For today's discussion, we're going to assume they have roughly the same stability, the CH and CE bonds. So we're going to start here with our reactants, and then we're going to end at the same height with our products. This is a potential energy diagram. And we already know it takes a substantial amount of energy to lose the aromatic stabilization energy. So that would be an endothermic process. And seeing the shape of our diagram, maybe I could have planned it a little better here. There. Okay. Stretch it out a little bit too. There. Nice. So we're starting with benzene and some kind of super electrophile. And you're saying, okay, do we have to overcome all 152 kilojoules per mole of resonance stabilization energy? And the answer is not really. This thing, even though it's a cation, which we know is not stable, it does resonate. It doesn't resonate in an aromatic fashion because there's an sp3 carbon in the way, but you can resonate and draw other resonance forms, which enhance the stability of this cation. One such resonance form would be here. And you'd have this species here with the double bonds here and here, and the cation there. And another I'll draw without the mechanism. Well, I can draw the mechanism arrows. We could just resonate here and generate a third electrophile. So quite a bit of resonance. It's not as good as aromatic resonance, but it's not terrible either. 3 resonance forms. I think you'll remember this kind of resonance is just called allylic resonance. ALLIYLIC resonance. And it makes the barrier somewhat less than 152 kilojoules per mole to get to our cation here. And you got your cation there. And then it reacts with some kind of a base. And the reason this is so exothermic to go from cation to final product is that you're getting your aromaticity back. So this process here, as is indicated up here, is re-aromatization. And it is lightning fast. And electrophilic addition, because it has such a high barrier, is really slow. Compare this barrier here to go from the reactants to the top of the hill to this barrier here to go from these reactants to the top of the hill, and you can see that this is going to be a lot faster than that. And I don't think much more needs to be said in terms of potential energy here. This mechanism covers a lot of mechanisms in this chapter. The only variation is our generation of our strong electrophile, which we'll explore on the next couple pages. Or maybe on the next page, see if we can all get them all in one place. So let's, without further ado, move on to that. And here are the 5, or really 6, if you're looking carefully over here, there's 2 categories. 6 electrophiles we have to generate. And I don't think you've seen a chlorine cation or a bromine cation before. That is not their nature. These have to be generated under very rigorous conditions. So let's look at what kind of things have to be done to generate those. We'll go downwards on this page. We could start with bromine, itself a very strong electrophile already, not strong enough for benzene to react with it. It needs to be souped up. We're going to soup it up by reacting it with an even stronger Lewis acid. And we're going to use FeCl3. This is a highly oxidized iron. It looks pretty innocuous, but it is very reactive. You put FeCl3 in water and watch the pH plummet because the reaction will generate HCl. But we're not using water here. Well, yeah, these are aqueous reactions, but water's not important in this discussion. Bromine is going to do this. Instead of acting like an electrophile, it sees this highly positive iron and it acts like a nucleophile. You've actually taken a normal electrophile and made it act like a nucleophile by presenting it with something that wants electrons more than the original bromine does. Bromine loves accepting electrons so it can break this bond. That's its normal behavior that we've seen many times. This is abnormal behavior because of the presence of this very positive iron. And what's happening here is you're going to generate this species which will not last very long, very ephemeral. That is an iron anion now. We call those complex ions, if you remember from your inorganic days. And the bromine in the middle is a cation. And it says, maybe I can grab these electrons and become neutral, and it does. And I'll draw it over here. Bromine is attached to FeCl3. That's a complex ion. And we also generated, as promised, Br+. We'll highlight it. That's our super electrophile. Generation of electrophiles. Our short form for electrophiles was E+. And we'll highlight that one too. How do we generate NO2+? I'm going to steal a little bit from the notes in the future here. At the next segment, we're going to put this to practice, so I'm going to feel free to steal my own work here. We have the two pieces needed to generate NO2+ right here. And we're going to go back. There they are. We have nitric acid, HNO3. And here is where it becomes apparent that Dr. Whitaker did simplify your life a little too much in chapter 4 for good reasons. Sulfuric acid is a stronger acid than nitric acid, even though we learned they have the same pKa. That was a bit of a fib. Sulfuric acid has a slightly lower pKa. And you can induce it to lose water in a simple acid-base dehydration. And we're going to use our typical red first, blue second. And we're going to protonate the OH on nitric acid to make it a better leaving group. And I hope you're noticing nitric acid just acted like a base. My goodness. You took a strong acid and made it act like a base. That's insane, isn't it? But hey, when you have a stronger acid present, nitric acid doesn't have a choice. And then after that, it can eliminate and generate the thing you see at the top of the screen. So it lost water and it made that species up there, which is your electrophile.
Doctor?
Yes.
When you did this mechanism, are we supposed to break the pi bond between the N and the O first?
Oh, you're good. You're a good student. You've been listening. You're making me proud right now. Yeah, if you wanted to be even more accurate with your description, you could do this. And I would be perfectly happy if you did this. You could break it down to 2 steps. And you could say, all right, I'm going to protonate up there. And I'm going to resonate. And resonance can be combined with that. So you really don't need 2 colors here. And there's your pi breaking as you're making a new one. And that doesn't quite get rid of your leaving group, does it? So you have more work to do on this one, which it's okay. This is probably more accurate. So now I got 2 OHs up here. And you'd have to protonate and then make it leave. More sulfuric acid here. Oh, it's in black, sorry. Protonate first. Make leave next. Oh, and we'd have to lose an H too. I just made this mechanism much longer, didn't I? So protonate to make a better leaving group. Grab the H, make a pi. And there you go. I think you're going to like this one better, aren't you? But pi's do break before sigmas. So pi's breaking here and reforming a new pi bond to compensate. And I have a formal charge violation there, and I'd be in trouble. I want to test if I did that. And I'm missing an arrow down there. This is an OR option. I would stick with the top option. Protonate, make leaving group, make leave, consistent with our dehydration mechanisms of the past. And our next electrophile is SO3. You're saying, wow, can sulfur do that? It's got octet violation. Oh yeah, sulfur's in the third row in group 6. It can make up to 6 bonds if it needs to become neutral, and it has done that. And this is a pretty cool mechanism. The only chemical involved is sulfuric acid. If you heat sulfuric acid up, it will auto-dehydrate. What does that mean? It means sulfuric acid acts as a catalyst for its own dehydration. So a little heat is always required here. And you're going to need the conjugate base of sulfuric acid to grab the H, which is always present when you have sulfuric acid. Why? Because sulfuric acid's a strong acid. Strong acids are always in equilibrium with their conjugate base. And our first step, if you're going to make water leave, you guessed it, protonate the O to make it a better leaving group. And then grab the H, make a pi, and I guess I don't need an arrow going downwards. This is going to make what we want up there. And we're going to highlight it. SO3, we'll see how it reacts shortly. And of all the electrophiles, this is one that seems to be the one without a plus charge. Does that make it less reactive than the other electrophiles? It does not. Sulfur is as positive here as any atom on this page. It has 6 bonds to a more electronegative type of atom. That is as good as being a cation. Tidying up here. Okay. So we have 3 types of electrophiles, halogen cations. Down here, nitrosyl carbocation, nitrosyl cation, sorry. And I even misspoke about that. That's a nitronium. Nitrosyl cation we'll see next chapter. I better write this down. Nitronium. Sulfur trioxide. How did you make sulfur trioxide? You dehydrated sulfuric acid. Another way to generate sulfur trioxide, burn sulfur in coal. What does it do? Oh, it reacts with water in the air and makes sulfuric acid, contributing to acid rain. Carbocations we've generated before. We'll show you a new method, but please don't forget your old methods of generating carbocations, because those methods still work. And if you can generate a carbocation by, say, reacting a pi bond with a strong acid, then that too could be an electrophile for electrophilic aromatic substitution. But here we're going to use alkyl groups attached to halogens like chlorine. So let's do this one down here. And things are getting crowded up here. I don't know. Can I move stuff? Yeah, I got my arrow there. There we go. Got this rogue too. All right. Let's do a carbon that could be a secondary carbon. Could be secondary, could be tertiary, could be anything. R, R prime, R double prime. Okay. Normally we think of that as an electrophile, right? We analyzed it as an electrophile in chapter 9. We said tertiary carbon's going to become a carbocation and do an SN1, or a primary carbon is going to have a backside attack and do an SN2. You remember that? I hope so. Here we're going to make it into a carbocation by pulling off the chlorine. We're going to use a Lewis acid, much like we used iron 3 chloride over here, except iron doesn't do a great job. We need an even stronger Lewis acid. Yes, aluminum chloride is an even stronger Lewis acid. Don't believe me? Try putting some aluminum chloride in water. You thought this thing was dangerous. Not only as soon as you open the bottle of aluminum chloride does it start giving off white smoke, but you put it in water, it starts fuming and generating white smoke called HCl, hydrochloric acid. It's a very powerful Lewis acid. So the first step would be to make the normal electrophile act like a nucleophile, because this thing really wants electrons. And after this step, you've got some options. You've got your 3R groups. You got your Cl, that's now a cation, and it's hooked up to an aluminum that's an anion now. Aluminum, much like boron, when it has 4 bonds, it's an anion. And you have the two options of if R equals R prime equals, let's not say it that way. If R prime and R double prime equals C, then you know what this thing wants to do. It's going to do this. And you're going to make a nice carbocation. If these are all C's, what's your category of carbocation? And that's the answer, tertiary carbocation. And what's the other species? Well, you got a Cl with this aluminum complex ion. And that's the story if R prime and R double prime equals C. Now, if R prime equals H and R double prime equals C, here's your result. No reaction. Primary C plus is illegal. That's your reasoning. And that would be a primary carbon if it had only one carbon attached. And the third story, multiple stories here for this one. If all of them are H, it's not the end of the world. If R prime, R double prime equals H, no reaction, but I'm going to put an asterisk. The electrophile is the species you drew earlier. This species right here, that will be your electrophile. So it can get a highlighter on it. We have to point out, I'll use a, I don't know, different color highlighter. Bad choice, green for this example, baby blue. So if that's the case, then this thing here is your electrophile. It's going to take a lot of highlighting. And we'll see on the next page and the next segment how that behaves. And if we have tertiary, then that's your electrophile. Primary, you're out of luck, but you're not really. We'll talk about primary very shortly. And what time we got here? Yeah, we'll do the mechanisms as our segment 2. And then we'll pick up with directing effects as segment 3. So I will see you very soon.